We're going to revisit our discussion of the free fall kind of motion that we talked about back in chapter 2, except that now we're going to allow the object that is rising and or falling just under the influence of gravity to move in 2 dimensions. So it might take sort of a parabolic path that's shown in this little cartoon here. And we want to analyze the motion just as we did back in chapter 2. So in order to be definite about it, we're going to put some axes on here. I'm going to define x to be horizontal, y to be vertical, and let's suppose that we call t equals 0 the moment the ball is initially in free fall. That means that gravity is the only significant force that's acting on it. Just before that, it was in contact with the person's hand, so there would be a hand force too. But t equals 0 is supposed to be just after it leaves the hand. In this case, what we would like to find is the x and y coordinates of the ball during this whole time when gravity is the only force on it as functions of time, where t equals 0 is when it's first free. Now, we already know that when something is either dropped or thrown upwards, it accelerates toward Earth at 9.8 meters per second squared. The same thing is true even if it's thrown at a slight angle, so it undergoes sort of an arc-shaped path like this. The acceleration at every point during the path points directly down towards the center of Earth, and it has magnitude 9.8 meters per second squared. So the length of this acceleration vector that I'm showing right here is 9.8 meters per second squared. And that means that because of the directions we've chosen x and y as, this acceleration vector has 0 x component, right? And going from tail to tip, we don't have to move along the x direction at all. We only move along y. And in going in the y direction from tail to tip, y is decreasing. We're going in the negative y direction. So the y component is negative. That's just, we didn't have to choose plus y is up, but that's how it comes out here. And its magnitude is 9.8 meters per second squared. So this is another example of, we already talked about constant acceleration motion being a special case that we are interested in one-dimensional motion. Here, when we talk about constant acceleration, we mean the entire acceleration vector is constant. And when we say the vector is constant, that means that both the x and y coordinates, components are constant. Because if either one of them were changing, the vector itself would be changing. So constant acceleration motion, this is one very important special case of it. And generally, when things are moving in 2 dimensions like this, they could even be going straight up and down. That general motion is called projectile motion. So it's like you're firing a projectile, which is a ball in this case. Now, the same calculus argument, or I think in Giancoli he actually gives geometric arguments for simple kinds of cases where the acceleration is constant. We can repeat the argument that gave the 3 kinematics equations before, starting with the assumptions that both ax is constant and ay is constant. And we get actually 2 different and it's sort of exact copies of the kinematics equation. So if the x acceleration is constant between t equals 0 and some later time t, then these 3 familiar kinematics equations still hold. And similarly, the assumption that ay is constant between them, producing the same argument again, gives the same set of kinematics equations, but notice the important difference is that everywhere there's an x on this side, there's a y on this side. So all the x's over here change to y's. And that's somewhat interesting because that's telling us that how things move, as long as the acceleration is constant, of which this projectile motion is an important special case, how things move along the x direction as a function of time is totally unaffected by how they're moving in the y direction. Sometimes this is referred to as the independence of motion when things are in projectile motion, independent of horizontal and vertical motion. So for example, here's a picture I stole from the web of cannon up on a cliff, and the cannonball is fired, and it follows this path going down here, right? In this case, we would say, look, it's accelerating along the y direction. It's not accelerating at all along the x direction. Ax is 0, just like it was in the previous cartoon. And the independence of x and y motion means that in this case, if we, instead of shooting it with an initial velocity going outward like this, if we just dropped the cannonball, it would be at exactly the same heights at the same time as it was if we shot it outward versus just dropping it. So that means the vertical motion doesn't depend on how we started out the horizontal motion. And similarly, if we could somehow turn off gravity so this ball were not accelerating at all in the downward direction, at each time it would have exactly the same horizontal position. The vertical motion, of course, would change because if gravity were turned off, it would just go along a straight line. But at each time it would be at exactly the same horizontal position it would have as if we had gravity there. So the horizontal and vertical motion kind of are independent of each other, and that's somewhat convenient because sometimes we can solve problems by just looking at one and the other. But notice, the t appears in both sets of these equations. So sometimes you'll have to use both the x and y information. That's very common in order to work in a t or something like that to solve for the one that you want. If you want to know something about y, you might have to actually address the x equations because they might help you find t from some information that's given. Here's another picture kind of showing the same thing. Here's a ball that's being rolled off the edge of a table at a very small initial velocity, medium initial velocity, and large initial velocity. And the idea is at every time after it leaves the edge of the table, it's at exactly the same height. So the progression along the y direction doesn't depend on how it's progressing along the x direction. These three balls are progressing at different rates in the x direction. That has no effect on their y direction motion. And that's just a function of the fact that the x's only appear over here, the y's only appear over here. Now, applying these, it's crucially important to notice that the assumption that the acceleration is constant means that gravity can be the only significant force in between t equals 0 and the later time t. And that means that if someone is throwing a ball up, you can't include the time that their hand is in contact with the ball. Or you can't include the time that the cannon is actually pushing on the cannonball to get it started. Or you can't include the time when the ball is still rolling on the table, because all of those cases, I'm appealing to your intuitive notion of what a force is. The cannon is exerting a force on the ball. The hand is exerting a force on the ball. The table is exerting a force on the ball. And that means that gravity is not the only significant force that's acting. So, and the same thing applies to when it hits the ground. We can't include the time when it hits the ground. Then all of a sudden the ground force on the ball, ground is pushing on the ball to slow it down very quickly, and gravity wouldn't be the only significant force. So you'll often see me in problem solvings taking something like the initial state is just after the ball leaves the person's hand. Just after, because we want to make sure it's not touching the person's hand. The final state is just before it hits the floor. You might want to say when the ball hits the floor, but that's a little bit ambiguous because there's a very short time when the floor is having a big impact. So I think this is a little bit more clear. Just after the ball leaves the table and just before hitting the floor could be our t equals 0 and our later time t. All right, so let's get into some examples. We're going to do one example together, and then I'll leave you to do a worksheet example on your own. The same kinds of concerns that we had with one-dimensional motions using the kinematics equations apply here. We need to be very clear about what our axes and where the origin of the axes, which way is plus y, which way is plus x, where's x equals 0, where's y equals 0, because that affects what x means, right? If you're talking about what x coordinate something has, we need to know where x equals 0 is, and so on. And if I want to know what vx0 is, I need to know which way plus x is, because if I choose plus x the other direction, vx0 would change sign. We also need to be very clear about what the initial and final times are that we're considering when we're applying these, right? These are valid for a certain period of time, and sometimes you might want to choose different initials and finals to answer different questions, but we need to make sure that AX and AY are both constant the entire time between the initial and final in order to apply these 6 sets of equations. Then it's always a good thing, just for problem solving's sake, to list out the symbols you're given. There's just a lot of symbols in here. Do we know the initial x at t equals 0? Do we know the initial x velocity component? Hopefully we know the constant x acceleration component, but there can be problems where that's the thing you want to find out, and so on. Do we know the amount of time that it takes to get from the initial time to the final time? Maybe that's given in the problem. And then finally, which variable do we want to know? And we really want to focus on that when we're looking at our kinematics equations and say, if I'm looking for y final, then I want to consider, first of all, the equations that include a y final, which would be these last 2 of the 6 right here, right? This includes a y final, and this one includes a y final. So I'd really just have to choose between those and then see where I'm at if I need any more information. Oftentimes, almost always in these kinds of problems, you won't be able to get away with just using one equation and solving it. We'll have to, choose one equation, maybe choose one equation, we'll see an example of this in a second, and say, well, I would be able to solve it if I only knew, for example, t. Then I'd be done. And then I can go over and look at the x information and see, well, is there some other equation over here that would allow me to solve for t, where I have all the other information? And then I can solve for t and plug it into the first equation and solve for the thing that I'm looking for. So here's an example that we'll do together. The fastest major league pitcher throws at 45 meters per second. I don't know if that's true anymore, but at the time I wrote this problem, that's what the web said. If we ignore air resistance, if the ball is released horizontally, so we're going to imagine the pitcher throws parallel to the surface of the earth, how far does the ball drop vertically on the way to home plate? So the person releases the ball horizontally, and it starts to fall. By the time it crosses home plate, it's fallen a certain distance from the release height. It's gotten closer to the ground. And here we're told that from the pitcher's mound to home plate, it's 18.4 meters. Again, that's something I looked up at the time I wrote this problem. So hopefully that's true for you baseball folks. So let's follow I'm trying to follow those suggestions that we had on the previous page. One of them was be sure to be clear about what your axes and origin are. So here I'm going to imagine the release point, in other words, the point at which the ball has just left the pitcher's hand, is this first red dot right there. And I'm going to make plus y is up and plus x is horizontal and toward home plate, and put the origin right at the release point of the ball. In other words, just after it's left contact with the pitcher's hand. I guess it does say ignoring air resistance here, so you should always be sure that air resistance is negligible. When things fall a long distance, that's often not true, or if they're fired at great speeds. It may not be a completely realistic thing in this scenario, but we'll take it at face value here. So choose axes and origin. So I drew a little cartoon. Here's the ball. It's falling on the way to home plate. Home plate's down here somewhere, and the ball has fallen a bit on the way to home plate when it passes it. I want to know this distance here. So if this is initial, when it's released, I'm being explicit about what the initial and final times are, and final is when it passes over the top of home plate, which is down here somewhere. What we would like to know is y final, right? Y initial is 0. I can see that right here. And y final, I'm expecting is some negative coordinate. And if I know y final, then if somebody asks me how far it drops, if I solve for y final and I get a negative number, normally, in normal conversation, if somebody says, how far does it fall? You don't give them a negative number. That would just confuse them. But I'm expecting to get a negative answer if I solve for y final, given my conventions that I've chosen for the axes here. And you could have chosen differently. It's just, nothing's any better or worse if you choose plus y is down. And you're welcome to try that, see if you can get the same answers out of the problem. You should, if you choose a different plus y or plus x direction, or even a different origin, then you should get the exact same answer in the final, for the final response to this. Okay, so we got our axes and origin, initial and final. What are we given? Well, in this case, given that the ball is released horizontally at a speed of 45 meters per second, that means Vx initial is 45, Vy initial is 0 because the initial velocity vector is going completely horizontally. Now it starts to head down, but initially at t equals 0, it's going completely horizontally. x0 and y0 are both 0, so we know those. X final in my coordinate system is 18.4 meters, right? Because between initial and final, it goes a distance of 18.4 meters, and it started at the origin. And ax is 0. It's not accelerating at all along the x direction. Ay is minus 9.8 because plus y is up, and we want y final. So that's you don't always have to write down everything you know and the things you don't want, the things that you want to know, but it sometimes helps when you're first doing these kinds of problems. It'll help structure it because there's just a lot of symbols in these kinematics equations, and it can be kind of befuddling to look at them. So, sometimes I'll go and circle the things that I know and then underline the thing I want to know and just see what's left. What do I still need in order to solve for what I want to know? Okay, so we need to pick from these. If we want to solve for y, we've narrowed it down. The only two equations that involve y's are these last two right here. Here's y final, and here's a y final right down here. Now, in the second to last one right here, we know everything in this equation except what we want to know, y, and t. We don't know anything about how long it takes for it to get over home plate. So I could phrase my predicament, if I choose this equation to go with it, that if I only knew the time that it took to get to home plate, then I'd be done, right? I'd just plug everything into the right-hand side and solve for y final. Now, you might have thought to choose the very last equation, and in that case, there's no t, but we also don't know Vy final there. We don't know how fast it's moving in the y direction when it passes home plate. And so you might look, well, could I find Vy final anywhere else here? And you'd see, well, in order to know Vy final, I need to know t, so I'd be no better off. It seems like this is the most direct way to go to start out. We're going to have to know t anyways. We may as well just go straight through this equation that I've circled there. So if I only knew t, how can I get t? Well, I haven't used the information about 18.4 meters anywhere. That's my x final, and it doesn't appear anywhere on this side. So I want to know something about x final. So the two equations that have to do with x final are this one right here and this one right here. And so if in this case, I know x final, I know x initial, I know vx initial, and I want to know t. So it looks like I know everything in this equation except t. So if I only knew t, I could solve and be done over here. And this equation on the left, the x versus t equation, allows us to solve and find t, because the only unknown, once we plug in everything we know in that equation, is t. Okay, so let's go back to the solution now. Let's work on this left equation, x versus t. Here it is written right here, and I'm going to start plugging things in. x0 was 0, so that first term goes to 0. And ax is also 0. It's not accelerating along the x direction, so that's also 0. Make sure you stay awake here. A lot of times people think, oh, when things are flying through the air, the acceleration is always 9.8 or minus 9.8. That's not true. That's true for ay for our coordinate system, but ax is 0. It's not accelerating horizontally. Okay, when I do that, there's only two things left, right? One on the left-hand side, one on the right-hand side. I'm going to plug in x final is 18.4, my coordinate system. Vx0 is 45. That allows me to solve for t. So t is a little bit less than half a second, 0.409 seconds. And then we weren't asked for t, but that's just my step on the way to now plugging into that y versus t equation. So I want y final. Y initial is 0, Vy initial is 0, so the first two terms go to 0. And then in the third term, Ay is minus 9.8 in my coordinate system, and we now know t, the time it takes to get between initial and final. So I'll plug those in here. Noting that Ay is negative, that gives me, as I expected in the beginning, that y is minus 0.82 meters. So, if you wanted to answer the question in a way a normal person would, you would say it drops 0.82 meters. If you tell someone it drops minus 0.82 meters, they'd sort of be confused and not necessarily know what to think. So once you've gotten your numerical answer, then you can just give a physical answer to the problem in the way that it was raised. All right, here is a worksheet problem on that. So that previous example problem is part of a worksheet, and I just thought we should work it out together because it's the first one we've done in a two-dimensional projectile motion problem. Here's one I want you to work on yourself, so we'll stop the video and you can try it yourself. Soccer ball is kicked from the ground at a speed of 22 meters per second and at an angle of 40 degrees above the horizontal. Okay, so we're saying horizontal would be 0 degrees. It's kicked up a little bit, but not quite 45 degrees above the horizontal direction. How much later in time does the ball hit the level field after it's kicked? So it's kicked up and it eventually comes down and hits the field. And how far does it go as measured along the ground from the kick point to the point at which it hits the field? So again, I'm giving you a hint here. This is a good idea for all of these kinds of problems. Draw a diagram. So you draw out the path of the ball as sort of an approximate parabola. Choose axes and origin location and compute the initial velocity components. And when we compute the initial velocity components, in this case, notice that that velocity vector, which has length 22 meters per second, is tilted up at an angle of 40 degrees above the horizontal. And we're going to need to break it into horizontal and vertical components in order to get our Vx0 and Vy0 to use in the kinematics equations. So that's one of the first things you're going to have to do. Try it yourself, and we'll be back with the solution.